Alright kiddos, welcome back. We're going to continue our discussion of hybridization and come pretty close, if not finish, our bonding unit for the day. So I want to talk about the Lewis structure for C2H4 and the hybridization of the carbon atom in C2H4. When I draw its Lewis structure, we end up with a double bond between the carbon atoms, and each carbon being bonded to two hydrogens like this. So if you look carefully, each carbon atom has 1, 2, 3, 4 pairs of electrons around it. 1, 2, 3, 4, so no big deal there. We also notice that each carbon atom has 3 regions of electron density. 1, 2, 3. And this carbon has 3 regions of electron density. 1, 2, 3. What did we say in the previous video about atoms, central atoms, that have 3 regions of electron density around them? Let's see, 3 regions of electron density give us what type of hybridization? sp2. Well, that's interesting because in the last video we showed carbon, when it formed the molecule methane, to have sp3 hybridization. Now we're saying it can also have sp2 hybridization. How does that work? All right, well, let's start with its electron configuration. Here's the electron configuration for carbon again: 1s2, 2s2, 2p2. The orbital diagram has, for the valence electrons, has 2 in the s orbital and 2 in the p sublevel. And of course, what if we bump one of these electrons up and then we hybridize an s with 2 of the p's? Now think about what I said. We're going to hybridize an s with 2 of the p's. So we'll have an sp2 hybridization. Then we're going to have a p orbital that's not hybridized. And each of these will have 1 electron in them. Now that's going to end up with a pretty interesting geometry. The sp2's, kiddos, are going to have this trigonal planar shape, as you recall, and they will be 120 degrees away from each other, and they'll each have 1 electron in them. Okay, no big deal there. And then this p orbital here that did not hybridize has this figure 8 shape with 1 electron in it. I know I'm drawing it in the top portion here, but it's in the top and bottom at the same time. The electron takes that wave pattern, kiddos. So we have an interesting situation here where we still have 4 valence electrons for carbon. 3 of those 4 are hybridized. 1, 2, 3, sp2 hybridization, and the other one's not hybridized. So what if 2 carbon atoms do this? Because after all, the formula is C2H4. So let's draw another carbon atom over here with the same hybridization. 1, 2, 3, each with 1 electron in it. Okay, so we do that in red. 1, 2, 3, and then a non-hybridized p orbital. So right like this. And once again, that has 1 electron in it. We'll put it down here at the bottom. Well, let's see. If these 2 carbon atoms come close enough to each other, can't we end up with a pair being shared right there? And then can't this pair up here sideways overlap? If they get close enough to each other, they can. And so we end up with this head-to-head overlap right here in the middle. Let's pick a different color so it shows up. This head-to-head overlap of hybridized orbitals, that is called a sigma bond. And then we have this parallel overlap of non-hybridized p orbitals, which we call a pi bond. So in C2H4, we have a double bond. One of those double bonds between carbon atoms is a sigma bond, and the other one is a pi bond. Once again, a sigma bond is a head-to-head overlap of hybridized orbitals, and a pi bond is a sideways or parallel overlap of non-hybridized p orbitals. So maybe this illustration here in my notes helps a little bit. Well, we're going to try it at least. Here's my carbon atom, and here's the other carbon atom. And do you see how this sp2 orbital and this sp2 orbital head-to-head overlap, and they share a pair? Remember, that's called a sigma bond. And then we have this non-hybridized P here with one electron in it, and this non-hybridized P with one electron in it. And if they get close enough to each other, we end up with a pi bond. Now we can see that a little bit better over here in the illustration right next to it. We have this parallel overlap of non-hybridized p orbitals, and that's my pi bond, kiddos. And then we have this head-to-head overlap of hybridized sp2 orbitals, and that's my sigma bond. Turns out that every double bond, it consists of one pi and one sigma. So a double bond has one pi bond and one sigma bond in it. All right, what about C2H2? Now C2H2, let me draw the Lewis structure for C2H2 for me at the bottom of this page. We have C triple bonded to another C, and then we'll have an H and an H over here. So notice once again that each carbon has 4 pairs of electrons around it, but this time each carbon atom has how many regions of electron density? Well, that carbon atom has 2 regions of electron density, and this carbon atom has 2 regions of electron density. What do we say about 2 regions of electron density? What's the hybridization there? Do you remember from the last video? 2 regions is sp. Oh, golly, wait a minute. Didn't we just say up here carbon had sp2 hybridization? And on the previous video with methane, didn't we say it was sp3? Can it also be sp? Well, apparently so. How does that work? Well, remember, when I merge the s with my 3 p orbitals, okay, 1 electron in each, what if only 2 of those hybridize? So we have 2 hybridized orbitals. Oh, let me go back here. S, p, and then we have 2 non-hybridized p orbitals. So each would have 1 electron in it. So what would these sp hybrid orbitals look like? Well, here's one of them. And wouldn't the other one be 180 degrees from it? Right? Each with 1 electron in it. Now this becomes a little bit more difficult to draw. We have these 2 p orbitals that are not hybridized. So what are they going to look like? Well, one of them, let's use a different color here, folks. One of them can be on this y-axis here with 1 electron in it, and then here's the tough one to draw. The other one we're going to draw coming in and out of the page. So if this were my x-axis right here for my sp hybrids, and this were, I guess we'll call it my z-axis for one of my non-hybridized p orbitals, the other one would be coming out in and out of the paper on this other y-axis. So that's really, really hard for me to draw. Hopefully the illustration above, when I get to it, will show that a little better. Well, there are 2 carbon atoms that do this, right? C2H2. So if the other carbon atom does it, it has an sp hybrid and another sp hybrid with 1 electron in each, right? And then it has a non-hybridized p that's on that axis, and then it has another non-hybridized p coming in and out of the paper. Right, each of these has 1 electron. If they get close enough to each other, can't we have a head-to-head overlap right here and have a sigma bond? Then can't we have a sideways or parallel overlap between these 2 p orbitals and have a pi bond? And then have another one with these green p orbitals and have a second pi bond. So we end up with a sigma and 2 pi bonds. And that's what a triple bond is. The triple bond is always 1 sigma and 2 pi bonds. Now let me try to show that in this illustration right here. So remember, we're saying that carbon has sp hybridization. Okay, so let me get a different color that shows up. So here's one here, and here's the other for that carbon atom, each with 1 electron. This carbon atom does the same thing. Oop, did you just see that head-to-head overlap there? Sigma bond. There's one over here. All right. Then it has two non-hybridized p orbitals. So let's try to keep my colors consistent. What did I use here? I think I used gray on one of them. So which one was that? That was the one that went up and down. So this guy here and this guy here, each with one electron in it. Put one up there and one down there. And then in green, oh, it's already green, so let's see. Green, we have a p here that's not hybridized and a p here that's not hybridized, each with one electron. And we can get some parallel overlap now, right here between these green ones and right here between these gray ones. So we end up with a pi bond and another pi bond, and right here in the middle, kiddos, is my sigma bond that makes up my triple bond. Okay, so once again, we take a look at the center atom. How many regions of electron density are in that central atom? If there's two, it's sp. Let's put that a different color so we can see that. Take a look at the central atom. If there are two regions of electron density, kiddos, it's sp. And for carbon, then, it must have two p orbitals that are not hybridized. They can still become involved in bonding, but not head-to-head overlap, only parallel or sideways overlap. All right, let me just wrap this up by maybe giving another example off to the side here. What if I had this molecule here? We do this a little bit more at the end of the year when we do organic chemistry. Let's say I had C bonded to C and a double bond here and a triple bond here. Okay, now this carbon can make one more bond, so we're going to put an H there. This carbon, oh, look, I messed up. I have too many bonds here. 1, 2, 3, 4, 5. That can't exist, can it? Whoops, let's try this. C bonded to C, a double bond here, and another double bond there. There we go. That looks better. So this carbon can have two hydrogens bonded to it. This one can't have any more because it already has 1, 2, 3, 4 pairs around it. This carbon has 1, 2, 3, so I can put a hydrogen here, and this carbon can have 3 hydrogens stuck to it, it looks like. All right, so let's practice this a little bit. What is the hybridization for this carbon atom, this carbon atom, this carbon atom, and this carbon atom? Well, let's count regions of electron density, shall we, around that center atom? 1, 2, 3, 4. That one shows sp3 hybridization. How about the one right next to it? Let's use a different color. We'll go red. 1, 2, 3 regions. So 3 regions is sp2. Remember, that double bond just counts as one region. So take a look at the carbon atom next to it. I think the gray will show up. We have 1 region, 2 regions. That's it. So that's sp hybridization. And then the carbon atom on the other end, let's use black. It has 1, 2, 3. So that carbon is sp2 again. All right, how many sigma and pi bonds do I have in this molecule? Sigma and pi bonds in this molecule. Well, it turns out that all single bonds are sigma bonds. And double bonds, remember, have 1 sigma and 1 pi. And triple bonds have 1 sigma and 1 pi. But we don't have any triple bonds in this one to worry about. So let's count up our sigma bonds. I'm going to use yellow, I think, for this one. 1, 2, 3, 4, 5. One of these, 6. One of these, 7, 8, 9. So I have 9 sigma bonds. That yellow didn't show up very well. Let me write 9 sigma bonds. Now let's count up our pi bonds. Remember, in a double bond, one of them is sigma and one of them is pi. So we have one of these is a pi and one of these is a pi. So I have 2 pi bonds. So I should have 11 altogether. 9 sigma and 2 pi. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Looks good. All right. Hopefully that made a little bit of sense to you, and we will move on from bonding finally with our next video. Nice to have you. Bye-bye.